So welcome. Today we'll be looking at metabolism of fatty acids. So, okay, let me get rid of this. So, fatty acids, remember fatty acids are the building blocks of lipids. You have fatty acids and glycerol, they make up your lipids. So, fatty acid is activated to form a fatty acyl CoA. Okay, this activation takes place in the mitochondrial membranes where we have three enzymes: an acyl CoA synthase, carnitine acyl transferase 1 and 2. So that I will not look today, but I urge you to look at it. So examples of fatty acids include lauric acid. You also have myristic acid, palmitic acid, palmitoleic, stearic, oleic, linoleic, and linolenic. So let's look at this. Lauric is a saturated, no double bonds, but it has 12 carbons. Myristic is also saturated, no double bonds, has 14 carbons. Palmitic, saturated, 16 carbons. Palmitoleic is a unsaturated since it has one double bond at carbon number 9. Stearic is saturated, no double bonds. Oleic is unsaturated since it has 18 but one double bond at carbon number 9. Then you have linoleic, which is unsaturated, 2 double bonds, one at carbon number 9 and another at carbon 12. Then we have linolenic, unsaturated, 3 double bonds, 9, 12, 15. So you should look at these two, linoleic and linolenic. So don't confuse the two of those. Okay. So once it is activated, it enters. This metabolism strictly takes place in the mitochondrial matrix. It is a mitochondrial process, does not take place in the cytosol. So let's see how it takes place. So this is how it takes place. This is now our fatty acyl here. Let me point at it. So this is our fatty acyl CoA. This. See here we have a CoA, coenzyme A is attached here at carbon. This is our carbon number 1, the carbonyl carbon, carbon number 2, number 3. So then we have, this is the terminal one. So this carbon number 2 is also known as the alpha carbon, and carbon number 3 is also known as the beta carbon. So you will see the reason why we are calling it beta oxidation. Okay. So this oxidation involves just 4 processes, 4 reactions. So let's look at those reactions. So what they are. So let's look at those reactions. So once let's look at this. Can you look? Here, the first enzyme here, fatty acyl CoA undergoes dehydrogenation, removal of hydrogen, by this first enzyme, which is known as the acyl CoA dehydrogenase. Okay, acyl CoA dehydrogenase is FAD linked. Okay, so here you see we remove 2 hydrogens. Which hydrogen? We remove one from here and another one from here. Okay, so you will make a double bond here. So you see after removal, you remain with one here and the one here. So with that, you have a double bond. This is the double bond here, as you can see it, the double bond there. Okay, so that is dehydrogenation. Remember, FAD will go to the electron transport chain, where it will yield how many ATPs? 2. So next, after now this compound now form will be known as trans 2. enol CoA. Remember, this is a carbon number 1. 2 shows the position of the double bond. Why are we calling it trans? We are calling it trans simply because why are we calling it trans? Because in these hydrogens here, see this hydrogen here and this here, one is located at here and the other one is located here. Sorry for that. One is located up there, the other one is located here, down here. So they are in trans position, opposite. So, and the double bond is at carbon number 2, so that is why it is called trans 2-enol CoA. So the second reaction after dehydrogenation, remember we transform the fatty acid CoA to a trans 2-enol CoA. Then in the other reaction, see here, addition of water. What do we call addition of water? What is addition of water? Hydration. Hydration. Okay. So we hydrate by an enzyme known as the 2,3-enol CoA hydratase. Okay. I want you to see where the water is added. So remember, water is a hydrogen and an hydroxide group. So you can see the hydroxide group comes and attaches to the beta carbon and the hydrogen attaches to the alpha carbon here. So you can see here, this hydrogen is still here, it's the same. But here we added another hydrogen to get 2 of them. Then this hydroxide group is added there. So that is that. Then after that, after formation of the 3-hydroxy, now this compound form is known as the 3-hydroxy acyl CoA. 3 why? Because you can see the hydroxide group is at carbon number 3, carbon number 1, 2, 3, or another, you can find also people calling it beta hydroxy acyl CoA. Beta because this is the beta carbon or the 3 carbon. Then we carry out the second dehydrogenation. Remember, the first dehydrogenation was FAD linked. Okay, so this is the second one. This is the second one, which is NAD linked. So the enzyme involved here is the 3-hydroxyacyl CoA dehydrogenase, also known as the beta hydroxyacyl CoA dehydrogenase. Remember, NAD goes to the electron transport chain and produces 3 ATPs, not 2 like FAD. NAD means the nicotinamide adenine dinucleotide, but FAD was flavin adenine dinucleotide. I will show you later. Then after dehydrogenation, we form this now this other compound here formed now after dehydrogenation is known as the 3-ketoacyl CoA. So I want you to show you where the hydrogens were removed. We remove this hydrogen here. Let me point it. We remove this and this. Okay. So all the hydrogens removed are for the beta carbon. So after removal, you see, we will form now the only oxygen will be attached to the beta carbon. Addition of oxygen is oxidation. So, and it is at the beta carbon. So you can see where the name beta oxidation comes. So the last step here, the last step involves the cleavage, is a cleavage step. What do I mean by cleavage? This can see here, we add a CoA. Okay, now the CoA will cleave we'll break this bond here. Okay, once it breaks there, remember CoA, it has a thiol group, an SH group. Okay, maybe I should maybe add it here. It has an SH group. Okay, so this hydrogen here, will be attached. It will escape from there and be attached here. So they were H2, now they become H3 as shown here. And this now, the remaining CoAs, it is not CoAsh. The hydrogen has been removed. It will be attached to here, where we cleaved. So you can see the rest is attached here. Here it comes. So you see, at the end of the day, we will have a fatty acyl CoA, which is 2 carbons shorter, and an acetyl CoA. No, remember, acetyl CoA will enter the Krebs cycle, where it will give us a 12 ATPs. Maybe I can show you that one. So let's look how many ATPs are generated from, let's say one of the fatty acids. So let me clear out this. Yes. So 16 carbons. This is a palmitic acid. Okay, 16 carbons. So remember, I've said now to convert from 16 here, convert it from 16 carbons to 14 here. This step here illustrated here. This is the now beta oxidation. So this is palmitic, 16, 14 will be myristic, 12 laulic, 10 caplic, 8 caplilic, and so on and so forth. So this is the beta oxidation. Let me first clear and show you it is beta oxidation, just like the one you have looked here. See, FAD, the first dehydrogenation, where we use the acyl CoA dehydrogenase, which was FAD linked. Then here we have hydration, where we use the enol CoA hydratase enzyme. Then we have the second dehydrogenation, where we use the hydroxyacyl dehydrogenase. Then we have the cleavage, where we use the thiolase cleavage. Then you get your acetyl CoA. Acetyl CoA is 2 carbons, and a fatty acyl CoA, which is 2 carbons shorter. Now let's calculate the number of ATP produced. Now, from beta oxidation, okay, from beta oxidation, FAD will give us 2 ATP. This NAD will give us 3. So for every beta oxidation step, we will have 5 ATPs. Okay. So maybe I should show you that. So from FAD we'll have 2 ATPs, and from NAD we'll have 3. So when you combine 3 plus 2, 5. But how many beta oxidation steps will we carry out? How many? So let's say it is this. It is 16 carbons. So imagine you have 16 carbons and you are removing two carbons for each. Let's call these passes. A pass is the beta oxidation step. So for every pass, you remove 2. So how many passes will you have to pass through? How many passes will you have to pass through to until you get a 2 carbon compound, the acetyl CoA? So it will be Here we have, this is 1, 2, 3, 4, 5, 6, 7, not 8. Not 8 because you cannot furthermore cleave the 2 carbons. So you will have 7 passes to cleave palmitic acid to an acetyl CoA. So for every pass, remember 5 ATP are produced. So it will be 7 times 5. 7 times 5, 35. Good. So 35. Remember, but 14 of the 35 will come from FAD, the 7 FAD produced, and 21 will come from the 7 NAD produced. So 14 plus 21, I think should be 35. Yes. Then all this, the acetyl CoA produced, this they are representing this way here. This acetyl CoA produced will enter the Krebs cycle. Remember the Krebs cycle? Maybe I should show you just a quick, where I show you Krebs cycle where the 12 ATPs were being produced from. So the Krebs cycle, this is the Krebs cycle here, also known as the tricarboxylic acid cycle. It has very many names. So you can see your acetyl CoA here will combine with oxaloacetate. Then this enzyme is citrate synthase. We form citrate. Then citrate is converted to isocitrate by aconitase. Then this is where the first dehydrogenation step occurs here. You can see here, right? The first dehydrogenation step catalyzed by an enzyme here, an enzyme known as the isocitrate dehydrogenase here. Isocitrate dehydrogenase dehydrogenates isocitrate to alpha ketoglutarate. Sorry for these are hiding. This is alpha ketoglutarate. You can see here NAD, we get an NADH. Then another dehydrogenation step here, alpha ketoglutarate to succinyl CoA. Succinyl CoA, also we have another NAD. Then succinyl CoA is converted to succinate by the succinyl CoA synthetase, where I want to show you this reaction is GDP linked. See, we put in a GDP, we are going this direction from succinyl CoA to succinate, where we put in a GDP plus a PI. This is a substrate level phosphorylation. We get a GTP. A GTP can phosphorylate and can phosphorylate a ADP to form an ATP. Then from succinate to fumarate, we have the succinate dehydrogenase, which is FAD linked, not NAD. Then fumarate to marate, we have fumarase enzyme here. Then from marate to oxaloacetate, we have marate dehydrogenase, which is also NAD. So from this, you can see we have three NAD produced. So for every NAD, remember, it's 3 ATP in the electron transport chain, which is coupled with the oxidative phosphorylation. So it is 3 times 3, that will give you 9. Remember, FAD will give you 2 ATP in the electron transport chain. So it will be 9 plus 2, 11. Then this ATP, so 12. So for every acetyl CoA we put in the Krebs cycle, we get 12 ATPs. So let's go back to our initial page. So yeah, you can see where now you can understand where the 12s were coming from. Okay, I hope you can understand where the 12s were coming from here. 12, and it is how many acetyl CoAs we have from palmitic acid? 16 divided by 2, 8. So it will be 12 times 8, 96. So if you add 96 and 35 or 14 are from FAD, 7 from NAD, and 12 from the 96 from the Krebs cycles, you will get 131. But the net, you must subtract 2 ATPs which were used in the activation, which I didn't look into. So the net production is 129 from palmitic acid. So for every unsaturated, for every saturated fatty acid, just ask yourself, how many passes will it have to pass through? Let's take stearic acid, 18 carbons. So it will be how many passes? How many? So you will, if you want to know how many passes, you simply do 18 minus 2 divided by 2. So it will be 18 minus 2, 16, divided by 2, 8. So it will go through 8 passes. For every pass, 5 ATPs are produced. So it will be 8 times 5, 40. But how many acetyl? Sorry for the confusion. How many acetyl CoAs are produced from stearic acid? 18 divided by 2, 9. So from every acetyl CoA, remember, we have 12 ATPs. So it will be 12 times 9 for the case of stearic, which is 108. Then you add the 40 produced from the passes. But during activation, 2 ATPs are used. So the net production from stearic acid is 146 ATPs. So you can see the longer the fatty acid, the more the ATPs we will get. Okay. So maybe I have something. Do I have anything else? Yeah, this annotation here. No activation of palmitic. This was a case of palmitate to palmitol CoA requires 2 ATPs, where an ATP is added to form an AMP and PPI pyrophosphate, which is usually we add water to get 2 phosphates, inorganic phosphates, by an enzyme known as pyrophosphorylase acts in this reaction. Oh, maybe I will look at that in another time. But for now, I guess I have come to the end. Maybe subscribe for more.